Okay, thank you everybody for joining me for this presentation. I'm going to talk about, sorry, I'm looking for my laser pointer. Okay, I'm going to talk about this. This is just about the concept of research. So I'm going to talk about smart, flat, right tuning. It needs some introduction, explanation. Let's assume that this is a car. This is the front of the car, back of the car, side, the other side. When we get excitation symmetric like a step or a bump, the front of the car goes over the bump and then the back of the car. This type of excitation put the system in this mode of vibration, which we call that pitch. You know that this is called pitch, this is bounce, and this is roll. I'm talking about pitch and bounce. Our goal is to transfer this type of motion to that type of motion. This is called flat ride motion. So there must be an adjustment for the front and rear suspension. Suspension means a spring and damper to transfer this mode of vibration to bounce. It started 100 years ago by somebody called Ole. This gentleman, Maurice Ole, who was the father of mechanical vehicle dynamics, actually, started in 1916, and he was doing a lot of research up to 1960, and then he established a new company. Now the company is running by his son, and anyway, they are working on vehicle dynamics, but around 1916, he developed an experiment like this on a Cadillac. This is a Cadillac. And as you can see here on the back, these are the weights, steel, metallic part to change the weight ratio. And here in side view, you can see that. Based on what he did experimentally, he gave us some recommendation. That recommendation is here. He said that it is better to have R squared over A1, A2 equal to 1. What is R squared? This is radius of gyration for this type of rotation. A1, A2 are the distance of mass center from the front axle, mass center to the rear mass center, which I showed it here. A1, A2. This is the front, this is the rear, this is the mass center. This is a mathematical model of the system that we are going to analyze. So that was first recommendation. The other recommendation was that the front suspension must be lighter than the rear suspension, means the spring on the back must be stronger. This mathematically, it says that here the wave is going faster, here wave is going to be slower, so vibration in the back will catch up with the vibration of the front because of the time lag between excitation of the front and excitation of the back. He said that probably 20% harder spring here makes the system better. So these are experimental results, but never done mathematically any proof, but all the companies were using this recommendation. There are some other recommendations. I'm going to skip that and concentrate on these two. Anyway, today I'm going to present a mathematical analysis of this problem. I'm not going to any nonlinearity, just everything linear, but you're going to enjoy the beauty of the mathematical analysis of this system. This is the system. We assume that the car is just a beam. We don't care about left or right, so we assume that it's a bicycle, a beam on two springs. We ignore the stiffness of the tire. So these are the main spring of the front, main spring of the back. Look at the generalized coordinate. We can assume bounce by x, pitch by theta, and this coordinate system gives me that equation of motion. As you can see, mass matrix is symmetric, diagonal, but K matrix is not diagonal for this set of coordinates. Let me change it to x1, x2 instead of x and theta. And if I do that, this is the equation of motion. In this system, which the generalized coordinate would be x1, x2, as you can see, K matrix is symmetric, mass matrix is not symmetric. Okay? We introduce some non-dimensionalization parameter based on these, which any of them are related to the parameter of the system, A1, A2, Mi, I is mass moment of inertia in pitch mode, and then K1, K2. Using these parameters, I can reduce the system to that shape, which has only alpha, gamma, capital gamma 1, capital gamma 2. So the number of parameter reduces to 1, 2, 3, 4 instead of 6, 7. Look at this shape, which is very beautiful shape. If alpha is equal to 1, then we get symmetric mass matrix. We already have symmetric K matrix. Again, if alpha is equal to 1, mass matrix would be symmetric, K matrix is symmetric, so it means the top equation and bottom equation are not going to be coupled. The system would be decoupled. Let's take a look what is alpha. Alpha is here, R squared over A1, A2. Remember the first recommendation of Ole, who said R squared over A1, A2, if it is equal to 1, we can get flat right. And this equation says that if alpha is equal to 1, we get symmetry. So with this recommendation, what we get is that actually the system works like that. The front and rear are totally independent, and mode shape of the system would be 1, 0, 0, 1, means in the first mode of vibration, the car is vibrating with the rear axle at the center of rotation, and then with the back, the front axle would be the center of rotation. These are the mode shapes, as you can see. Very interesting fact, and it says that what Ole found based on experiment works very well. So it makes the system independent, but still we don't have flat right. There are some other conditions that we have to introduce. But anyway, the first recommendation of Ole comes to our equation, alpha equal to 1, or R squared equal to A1, A2. Very interesting. Let's move on and see what we can do for better understanding of flat right. Again, back to the equation of motion of the system, like this, in matrix form, but this time I'm introducing damper as well. So we have here damping matrix. Also we have excitation, y1, y2, which here on the right hand side of equal sign, we see the excitation, which is a function of y and y dot, front and rear. But y1 and y2 can be, for example, a step input. So I'm going to optimize the system. When the car goes over a step, of course there is a time lag between front and rear. That time lag here is introduced by Heaviside function, which is t minus tau, and tau is a function of L over V. L is the wheelbase, V is the velocity, so L over V is the time lag between front and rear excitation. You're going to see that final flat right recommendation is a function of this parameter. Means at different speed, we can adjust the system to get flat right. It is not just one setup for every velocity. Innominate value are here introduced for normal cars. Take a look on mass, which is 420 kilo for half bicycle model. So actually the body was 840 kilos. And then A1, A2, L, which is wheelbase, K1, K2, C1, C2, and the other parameters. This is excitation. Let's take a look on Ole first condition, alpha greater than 1. Here you see the front of the system. Front of the system. Here is the rear of the system. As you can see, if alpha is greater than 1, this is what you see. Front vibration, rear vibration. While rear haven't seen the excitation, you see that there is vibration. And this is the pitch mode. It is getting 0 eventually because we have damper and we kill the vibration, but during the excitation time, we don't have flat ride. Look at this, alpha equal to 1. That's a magical number. When alpha is equal to 1, that's the front of the car vibration, and while the rear haven't seen the step, we don't see any vibration in the back, and then vibration starts here. This is the pitch, and we are going to back to this. This one is alpha less than 1, which is similar to alpha greater than 1, just vibration is opposite to the other one. So this is not our concern. Let's take a look on the equations of motion again with damping and excitation, as you can see. And then parameter zeta and k, I'm going to introduce new parameter. Look at k. K is k2 over k1, means the stiffness on the back compared to stiffness on the front. Let's assume that we set front stiffness and we are going to find the best k, which gives us the best k2. Also, zeta is damping on the back compared to damping on the front. Zeta is non-dimensional parameter, which are proportional to C1 and C2. Epsilon was a parameter I introduced in the back, which is related to mass ratio. So our job is to solve this, find the best zeta and k to get the best flat ride. So this is our job, to find the best of these two. The system is very simple. With that excitation that I set step input, we get the solution. This is x1, means vibration of the front of the car, and this is x2, vibration of the rear of the car. It is 0 while t is less than tau, which is L over V. After that, we get this excitation. So we have a solution for the front, we have the solution for the back. We have to match these two and kill the vibration. Let's take a look what I'm talking about. This is actually a good design solution. This is the first peak, second peak, third peak. Again, the black line here is vibration of the front of the car. First peak, second peak, third peak, fourth peak, and so on. X2 is vibration of the rear, and as you can see, X2 has a lag, and then theta is the pitch mode. Our job is to kill this. What we did, we set the third peak of the front and of the back be equal at the same time. You can match x1, x2 at any point you wish. The third peak is the only reasonable or earliest time that you can match these two. So our strategy is that x1 vibration, x2 vibration at the third peak be equal at the same time. This is what we said. Peak time, the third peak time for the x1 is that at that point x1 is equal to this. The third peak for x2 is this. This is peak time. At that time, x2 is that. So our job is to equate these two, equate that, these two. This is our condition. Based on this strategy, when you pick these two equal to each other, we get zeta equal to 1. That's the first result. Zeta equal to 1 says that damping in the front and damping in the back must be equal to be able to get this match. The other condition is for k. K is a little bit complicated. This is k. Z1 over Z2 tau squared and so on. Z1, Z2, Z3, Z4 are given here, which makes this equation complicated, but it doesn't matter. Computer can get the numerical values. But as you can see, k relates to mass, zeta, and also tau. Let's go to some plot. This is the plot. This axis shows tau. Tau was a function of velocity and wheelbase. So let's assume that we are designing a car which wheelbase is constant, so we are talking about different velocity. When tau was L over V, when tau is increases, means velocity is less. When we go lower tau, means velocity is faster. So faster, slower. Okay? And then K is the stiffness ratio between back and the front. This is the whole story of that equations that we found in the previous page, but it is not important because we are not working in everywhere of this system. This is epsilon A1 over L And this area is practical area. Let's take a look on that area. This is that area. Again, tau is usually between 0.1 to 0.9. And then epsilon, which is A1 over L, is between 0.4 to 0.6. You know that when A1 over L is less than half, less than 0.5, we have normal car, which is under steering system, which is stable. So majority of the cars on the street, maybe 99%, are here. A little percentage of the car goes beyond 0.5, something like 0.51, 0.52. So here, like Porsche, for example, which have engine in the back, so we have understeer cars. So my point is that this line is approximate 99% of the passenger cars in the street. Okay, let's assume that K1 is 10,000, which is nominal value, and this one says what K should be. Let me clarify. If, for example, we are driving with a speed that gives us 0.3 for tau, 0.3 was L over V, so velocity of the car, depending on wheelbase, there's no wheelbase here. Where is wheelbase? In the previous slide, I gave you a wheelbase. Wheelbase was 2 point something meter. Okay, at this speed, you go up based on your epsilon, you go left, and you find out how much stiffness on the back must be stronger respect to the stiffness of the front. For example, if I'm driving here and go find here, go here, it gives me around 40% stiffer. So this is how we design the system. Actually, we need a smart system to be able to adjust the stiffness on the back according to the speed of the car, not just one value. Okay, as you can see here, there are 3 different ratios for different value of zeta, 0.4, 0.5 was here, 0.3 is here, and 0.4 is here. Based on another analysis, we know that zeta equal to 0.4 gives us the best vibration according to the bounds. So I skip that one. These are just comparison of the equation that we found. But the smart system can adjust the K value according to the speed and the value of zeta 1. Let's assume that zeta 1 equal to 0.4 is the best. So this is what the computer in the system is going to use to adjust stiffness based on the speed of the car. So such a system, which is smart, is not actually a passive system. We cannot design any passive system. It means design a spring, a metallic spring, and put it on the car and make sure that the car is giving us a flat ride. It is not happening. It is working for a specific velocity. But if you are able to change the stiffness, like air spring, for example, according to one of these slides or curves, depending on how much stiffness, damping we have in the front and in the back, or how much mass we have and so on, then we are going to have a smart system. So we got to the conclusion. It means we get to the conclusion when we stop thinking or we don't have any time to go further. Finally, the conclusion is that OLE recommendation for this works very well. It makes the system uncoupled, and then just having a few percentage stiffer spring in the back with respect to the front is a good recommendation, but it is not working. We need a smart system to be able to adjust the stiffness of the back or front according to the length of the car and the speed of the car and other parameters like damping of the front and rear. These are references, and much better than what I said is published in this book a few years ago. In that publication, you're going to see what happens to this strategy if the damping is not linear. You know that in real system, damping of the car are not linear. It means bound and rebound have different curve of stiffness or damping. That's it. Thank you very much. Any question? Yes, sir.
So, thank you for great presentation. And so we all know about driving a car now and this flat. So your study refers to unit step impact.
Correct.
Okay, irregularity on the road. Like in the city, you drive and you kick the side of the road. That's exactly it, I guess. What about country? Because for that project which I did, I had to go to country. And guess what? I had a sinusoidal road like this, bumpy road, repeating for kilometers, and my car is oscillating more and more. How this relates to cases like that?
It's not possible. It's not possible if you have frequency excitation in front and in back. Depends on the velocity of your car, wheelbase, and where you get, at what phase you face the bumps. It always probably gives us pitch. The driver adjusts the velocity of the car to get rid of this. So it is a personal, training, but mathematically it's not possible.
So
we just give flat ride for a transient response, like going over a bump and get rid of this vibration to put it in that mode, and then damper are going to kill this even. So after a while we don't see any vibration. So it is just for transient, not frequency response.
So because really, that's very interesting, because
Yeah.
I saw this and road is exactly like this.
Correct.
When you visit these resorts, that's amazing. And your car starts oscillating more and more, depending on the speed, as
Right.
you say. You get it down, but it's really big problem.
Correct. Yeah.
So mathematically, it's not easy to analyze.
This analysis is not for frequency excitation. This is just for transient excitation.
Okay, very good.
Sure. Thank you very much.
Appreciate that.